In this series, we shall discuss the steps and regulation of secondary hemostasis and the associated pathologies. In this video, we shall talk about the physiology of secondary hemostasis and how this is regulated. Now, people view this as a rather convoluted topic, and we've all spent many hours trying to understand it and end up forgetting it. Here, I try to put it in simple terms for you so that you can recall all the need-to-know points when prompted. So what is secondary hemostasis? Well, its function is to stabilize the weak platelet plug of primary hemostasis through what is known as the coagulation cascade. Now, if you recall, in primary hemostasis, we have platelets expressing GP2B3A receptors, and fibrinogen binds to these receptors on individual platelets, forming a platelet plug. Secondary hemostasis wants to reinforce this plug, and it acts on the fibrinogen that links the platelets together. So, fibrinogen is the location of secondary hemostasis. And the end product of the coagulation cascade is thrombin, also known as factor II, which converts fibrinogen to fibrin, and thus stabilizing the clot. This will make more sense to you once we discuss the coagulation cascade. Before we get into the steps of the coagulation cascade, let us first list out a few important points. Number 1, coagulation factors are produced by the liver in their inactive form. And number 2, activation of these factors requires 3 important things. Number 1, exposure to an activating substance, which we shall discuss later. Second, a phospholipid surface, and in this case, this is the platelets. And third, calcium. And if you recall from primary hemostasis, calcium is released during platelet degranulation. Calcium can also be found in the serum. Okay, so now on to the coagulation cascade of secondary hemostasis. Now, there are 3 linked pathways of the coagulation cascade, and these are the intrinsic, the extrinsic, and the common pathways. I remember someone once teaching me a very simple way of remembering this. We all start with number 10. Factor 10 is the link between all 3 pathways. The maximum number that we have so far is number 12. So, in the intrinsic pathway, this contains the most numbers, and thus starts with the number 12. Then goes on to 11, skips 10, goes to 9, and then to 8. On the other hand, we have the extrinsic pathway, which starts with the number 7, or contains the number 7. So now we've described both the intrinsic and the extrinsic pathways. Now on to the common pathway. This is the simplest maths you'll ever do ever. 5 times 2 times 1 is 10. And this is it, in very simple terms. It should be very easy for you to recall, practice, and reproduce this. So, remember I said this requires an activating substance. Well, we start here with factor 12 in the intrinsic pathway. What activates factor 12 is exposed subendothelial collagen, so injury. As soon as injury occurs, if you recall from primary hemostasis, factor 12 is activated. Activated factor 12 then goes on to activate factor 11 and so on. In the extrinsic pathway, factor 7, associated with tissue factor, is activated by damage outside the vessel, hence extrinsic. Now, we have different lab tests that can measure the different pathways, and this is important to understand as these values could change if there is a deficiency in one of the factors or if the patient has been given an anticoagulant drug. The intrinsic pathway, remember, has the most numbers, has a test with the most letters, and this is the APTT test, also known as the activated partial thromboplastin time. This measures both the intrinsic pathway and the common pathway. On the other hand, the PT test, or the prothrombin time test, measures the extrinsic pathway as well as the common pathway. Finally, we have the thrombin clotting time, or the TCT, which measures the time it takes to convert fibrinogen to fibrin. So it depends on activated factor II converting inactive factor 1 or fibrinogen to activated factor 1 or fibrin. That was quite a lot to take in, so let us summarize it here. We have three pathways: the intrinsic, the extrinsic, and the common pathway. The end goal here is to make a fibrin clot. The intrinsic pathway is activated by subendothelial collagen, whereas the extrinsic pathway is activated by damage outside the blood vessel. The end goal is to reach factor 10. The intrinsic pathway contains factors 12, 11, 9, and 8, whereas the extrinsic pathway contains only factor 7. The common pathway is made up of the easiest maths in the world, that is 5 times 2 times 1. This all leads to a fibrin clot. The intrinsic and common pathways can be measured using the APTT test, whereas the extrinsic and common pathways can be measured using the PT test. Now, the anticoagulation drug that affects the APTT value is heparin, whereas the anticoagulation drug that affects the PT value is warfarin. However, this is expressed as the INR, but more on that later in the series. Just to quickly go over what we mean by the factors are released in their inactive form and describe to you how they are activated. So we mentioned to you how the intrinsic and extrinsic pathways are activated. Now, these activated factors, for example 12 and 7 at the beginning of each pathway, activate the subsequent factor. So for example, let's look at the common pathway. Activated factor 5 cleaves inactive factor 2 and activates it. So now we have activated factor 2. Then activated factor 2 cleaves inactive factor 1 and activates it. So now we have activated factor 1, which is fibrin. Now each of these factors does have a name rather than just a number, but I wouldn't really bother learning or memorizing these names. The ones I would remember are factor 1, which is fibrinogen, and factor 2, which is prothrombin. In their activated forms, these are fibrin and thrombin, respectively. So here we have factor 5 cleaving prothrombin to form thrombin, and thrombin cleaving fibrinogen to form fibrin. Now there is one other factor that we've not yet mentioned. This is factor 13, also known as fibrin stabilizing factor. Factor 13 is activated by thrombin, and its function is, well, in its name. Its function is to stabilize the fibrin mesh by cross-linking the fibrin. Now that we understand the coagulation cascade, we need to make things a little more complicated. The coagulation cascade needs to be regulated so it doesn't go off making random clots, and so it doesn't, quote, overclot. There are 4 natural anticoagulation mechanisms. These are, first, antithrombin, second, activated protein C, third, activated protein S, and fourth, tissue factor pathway inhibitor, or TFPI. Activated proteins C and S can be defined as one entity, so in fact there are 3 physiological regulators of coagulation. So let us start with antithrombin. This is a serine protease inhibitor, so it is an enzyme. Its function requires glycosaminoglycan heparins. Remember, we mentioned these to you in primary hemostasis, and they are expressed on the basement membrane. Importantly, the action of antithrombin is potentiated by the anticoagulant drug heparin, and it can be quite easy for you to recall this association and to remember it, because the antithrombin mechanism requires endogenous heparin for activation and is also increased and potentiated by the heparin drug. Now on to activated protein C. Protein C is activated by thrombin, and its activation is enhanced when thrombin is bound to thrombomodulin. And remember, we also mentioned to you in the primary hemostasis series that thrombomodulin is expressed on the basement membrane. This really reflects the importance of the basement membrane. Activated protein C then inactivates factors 5 and 8. It also induces fibrinolysis, but more on that later. So to help you visualize this, here we have damaged endothelial lumen, thrombomodulin is exposed, thrombin binds to the thrombomodulin, and protein C sees this and interacts with it, becoming activated protein C. Now activated protein C has a job to do. It goes off to inhibit factors 5 and 8, and also inducing fibrinolysis. Now protein S is a cofactor for protein C and enhances the activity of protein C. And finally, we have the tissue factor pathway inhibitor, or TFPI, that inhibits both factors 10 and 7. The way I like to remember this is that it starts with the letter T, so T for 10, and also the T kind of looks like a 7, so hopefully that helps you too. We mentioned that activated protein C also induces fibrinolysis. So fibrinolysis is the final step of coagulation. Its function is to remove the fibrin clot when it's no longer needed. Fibrinolysis starts with serum protein plasminogen. This is converted to plasmin by tissue plasminogen activator, or TPA. Now plasmin is a serine protease. This breaks down fibrinogen and fibrin into fragments known as fibrinogen degradation products, or FDPs. An important example of this is D-dimer, which is clinically measured in various pathologies. So, as soon as fibrin is formed, the fibrinolytic system is activated. Now, in addition to TPA, UPA, or urokinase plasminogen activator, produced by the kidneys, can also convert plasminogen into plasmin. So again, to help you visualize this, we start with fibrin, which is cross-linked by factor 13. Fibrin also activates the fibrinolytic system, so activates TPA and UPA. TPA and UPA convert plasminogen to plasmin, and then plasmin breaks down the cross-linked fibrin to fibrinogen degradation products, for example, D-dimer. And finally, and I promise this is the last part, fibrinolysis needs to be regulated. Its regulation is achieved by three main factors. First, plasminogen activator inhibitors 1 and 2, or PAI 1 and 2. Second, alpha-2 antiplasmin and alpha-2 macroglobulin. And third, thrombin activatable fibrinolysis inhibitor, or TAFI. Now there are other factors, but these are the main ones. So if we go back to our drawing, here we have PAI1 and PAI2 inhibiting TPA and UPA. Alpha-2 antiplasmin and alpha-2 macroglobulin inhibit plasmin. And finally, TAFI inhibits the action of TPA and UPA on plasminogen.